Okay, let's be problem solvers, shall we? If the point 5, negative 12 is on the terminal side of an angle in standard position, find the exact values of the 6 trigonometric functions. So they give me a point. I'm going to use a coordinate plane to help me plot that point. First and foremost, now before we even get started on this, a couple of things. Understand the context of the problem. When we were discussing in a previous video the anatomy, let's see if I still got it here, the anatomy of a trigonometric statement. We talked about how whatever the function is, this is an angle. The output from that is determined by the context of the problem, okay? So keep that in the back of your head. Now, in this problem, it says, we're dealing with a point that's in the coordinate plane that has coordinates 5, negative 12. So let's go 5, put it right about there, okay? So the terminal side of an angle is here, okay? So in standard position, the angle in question is this angle right here. But we've talked a little bit, we should have talked in class at this point. This is our angle, we'll call that theta, okay? In standard position measured in this direction. But all of the trigonometric functions values for theta and theta prime, the reference angle, are going to be the same, okay? So even though the angle in question is here, okay, we're going to be able to use a reference angle to find this out. And that's important because, let me draw this again, just for context. The unit circle, if the coordinates of this point are 5, negative 12, the unit circle is like right here, okay? So the point that they've given us is well beyond the unit circle. The point that's on the unit circle that corresponds to this terminal side is right here. And I don't know anything about that point. I do know that this point, 5, negative 12, is on the terminal side. So in the most simplest terms possible, we've blown past the confines of the unit circle. We're beyond all of those coordinates. So when we talk about this statement, right, where trying to evaluate trigonometric statements and getting values, that's the star, the output. If it's not going to be determined using these coordinates, then I'm going to shift gears and start talking about right triangle trigonometry now, okay? And if I'm going to be talking about right triangle trigonometry, I better have a right triangle. So we drop this perpendicular to the x-axis. And like I just said previously, our angle theta, right, is this angle right here. That's theta. But we're going to use theta prime to do this trigonometry, okay? Now we're going to break it, maybe not break, but we're going to bend some rules here. So we have a right triangle. We want to know, and this is our angle theta. We want to know what's the sine of theta, what's the cosine of theta, so on and so forth. Well, we can't say that the sine of theta is the y-coordinate. We can't say that the sine of theta is negative 12. This goes well beyond the range of sine. The outputs for sine are only from negative 1 to 1. You'll never get a calculator that tells you the sine of theta is negative 12. It's impossible. It doesn't fall within the range of the function, okay? For any number of reasons, we could expand on this over and over and over again, right? Here's just a quick one. Sine of any angle is the opposite side over the hypotenuse, that tried and true SOHCAHTOA, right? So if the sine of an angle is the opposite side over the hypotenuse, I can never create a triangle where the opposite side of something is negative 12 and the hypotenuse is 1, because the hypotenuse has to be the longest side. So use this as a very brief justification for why we don't just get to use the coordinates if those coordinates are outside the confines of the unit circle. So hopefully that satisfies some of your curiosity with this. Okay, so if we're not using the unit circle, then we're going to use right triangle trig. And if we're going to use right triangle trig, we need a right triangle. So here it is. Now, how am I going to find sine then? So now we are telling ourselves we're going to use SOHCAHTOA to do this problem now. Okay, so for this angle, we have to label the sides of this triangle. Well, this we know was that horizontal displacement of 5. Now we know this distance is 12, and here's where I say we're going to bend some rules, okay? I'm going to label this as negative 12. And they might take my math degree away for this, but understand that distances can't be negative. I know that, okay? I know that the distance from here to here is 12, right? I shouldn't be labeling this as negative 12. However, we've spent some time talking about how different trigonometric values in the context of the coordinate plane, different trigonometric functions have different signs, right? We talked about how in this coordinate, you have positive x values and positive y values. So sine values are, cosine values are positive, sine values are positive, and tangent values are positive. Now down here, we have positive x coordinates and negative y coordinates, right? So our sine values have to be negative. And when I use my Pythagorean triple here, if I may, right, we're going to have to do the Pythagorean theorem, but 512 is a Pythagorean theorem with 13. When I go to talk about this angle and I want to know the sine, the opposite side over the hypotenuse, it'll be negative 12 over 13. So we, by labeling that side length as negative 12 in this instance, we're sort of baking into our solution what's going to be negative and what's going to be positive. Okay. So again, distances like this can't be negative, but I'm going to label the negative distances as such so that when I use my SOHCAHTOA ratios, I don't have to think about, well, should this answer be positive or should it be negative? Okay. So there's that. The cosine of this angle would be 5 over 13, right? The adjacent side over the hypotenuse, both positives. Cosine's positive in quadrant 4, which is where this angle is. And then we have, I'm not going to change colors anymore. I'm just going to stay green if that's okay with you guys. We have tangent of this angle is the opposite side over the adjacent side. And then our reciprocal functions. We just flip all these over, right? Negative 13 over 12, 13 over 5, and negative 5 over 12. So here are 6 trigonometric functions for this. Okay, again, keep things in context. Draw the picture. We see that it's in quadrant 2. We're going to label this as a negative value because it is technically going down. Okay, and if we put that negative there, then when I go to use SOHCAHTOA, I don't have to think about, well, is it positive or negative? Okay, now this angle, okay, and I don't know what it is, right? And they didn't ask me for it. They didn't ask me for the measurement of the angle. They just wanted to know the 6 trigonometric functions. This angle right here, if let's just say it's, I don't know, in the neighborhood of 290 degrees. If you want to know what the sine of 290 degrees is, okay, that's going to be a negative number. Your calculator is going to tell you that the answer is negative. Okay, so that's why we have to have this context, this drawn in here with these negative values. Okay, so understand what we're trying to do here is we're trying to find a way to come up with these values, without a calculator and be as accurate as possible. Okay, so if we're not on the unit circle, we're using right triangle trig, and it all depends on the context of the problem.